This video is about working with multiple representations of a given situation. So in this lesson, we will begin to see the relationship between two different variables and start to write a function rule to describe relationships we can see in the real world. We will start by looking at a tiling business. So in this case, when we're looking at tiling a pool, the variables in this are the length of the pool, and the number of tiles. So if we have two variables, we can write a statement relating them. This is called a dependency statement. So in this case, we're always going to have something depends on something else. So when I think about the number of tiles and the length of the pool, if I want to put a border around the pool, the size of the pool is going to affect how many tiles I need. So we're going to say that the number of tiles depends on the length of the pool. So let's look at how we can model some situations of using a pool and tiling around its border. So Anthony decides to draw a model for the two smaller versions of the pool and for the larger version of the pool as well. Draw a concrete representation to show how many tiles are needed for a 1x1, a 2x2, a 3x3, and a 4x4 pool. So in this case, on a 1x1 pool, on all four sides, we're going to need one pool each to cover the length. Plus, we're going to need 4 more tiles that go in the corners for a total of 8 tiles. For a 2x2 pool, we need 2 tiles on each side to cover the length of the pool. Plus, we need 4 more in the corners to complete our borders. If I were to count these tiles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This gives me 12 tiles. For a 3x3 pool, we're going to need 3 tiles on each side of the pool to cover our length. Plus, I'm going to need 4, 1 for each corner in order to complete my border. So if I count my tiles in this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have 16 tiles. In a 4x4 pool, we're going to need 4 tiles on each side to cover the length of the pool. Plus, we're going to need 4 in the corners to complete our border. If I count the tiles in this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 tiles. So a concrete representation, then remember, is just a picture that shows what's happening in our situation. The next type of representation is a numerical representation. A numerical representation is always going to use a table. So in this table, we have pool in the length of the feet on the left. On the right, we have tiles of the border. So remember from above, if we had a 1x1 pool, we had 8 tiles. If we had a 2x2 pool, we had 12 tiles. If we had a 3x3 pool, we had 16 tiles. If we had a 4x4 pool, we had 20 tiles. So what pattern does the numerical representation problem reveal? Well, every time that our pool is gaining 1 foot in length, it's gaining 4 extra tiles in the border. So we could say for every 1 foot added to the length, 4 tiles are added to the border. So now we're going to use a table to help us create a function rule. A function rule can be used to determine how many tiles we need for a pool without having to draw them out. Especially when our pool sizes start to get really large, we don't want to sit there and draw out tiles forever. So what function rule would show the general relationship between the length of the pool of square tiles and the number of tiles in the pool border? Let's use our table. So remember when a pool had a length of 1, we had 4 sides that were a length of 1, plus we added our 4 extra tiles for the corner to get us 8 tiles. For a 2-foot pool, we had 4 sides that were 2 length for 2 tiles each, plus the extra 4 in the corners for a total of 12. For a 3x3 pool, we had 4 sides with a length of 3, 1 tile for each foot, plus 4 in the corners, which got us 16. For a 4 length, we had 4 sides that were 4, plus a corner of 4 more tiles, got us 20. So we can see that the pattern is we're going to multiply 4 for times the length of the side of the pool, because we have 4 sides, plus the 4 for the corners. So our function rule here is going to be t equals 4s plus 4. In our function rule, s is going to represent the pool length in feet. What is the number being added on? So this 4 over here is going to represent the 4 tiles needed to complete the corners of the pool. Remember, since the pool is a square, we have 4 corners that are going to each need 1 tile then. So our function rule is also called an algebraic representation. We can use this algebraic representation to find the number of tiles needed for a larger pool. So instead of sitting there and drawing this out, we now have our function rule, t equals 4s plus 4. And if we're given the size of a pool, we can plug that in for s. So for a 10 by 10 pool, we would have 4 times 10 plus 4. 4 times 10 is 40, plus 4 is 44 tiles. If we have a 15 by 15 pool, we have 4 times 15 plus 4, which would get us 60 plus 4, 64 tiles. This also helps us in a function rule is if we have a number of tiles, we can put that in for t to figure out the length and the size of our pool. So when we do that, we would set 52 equal to 4s plus 4. We can subtract 4 from both sides, so 4s equals 56, so now 52. And when we divide, we get s equals 13, which means the pool would be a 13 by 13 size. Now we're going to create a graphical representation, and we're going to use our function rule to help us fill in the table again. So our function rule is t equals 4s plus 4, and we're going to substitute all of our side lengths in for s. So 4 times 1 plus 4 gets us 8 tiles. 4 times 2 plus 4 gets us 12. 4 times 3 plus 4 gets us 16. 4 times 4 plus 4 gets us 20. So when I plot my points, I have 1 8, 2 12, 3 16, and 4 20. I'm not going to connect the dots in this line because we have pool in length of feet. All the tiles are coming in a length of feet, so we can't have intervals. We can't have little parts of a foot. We have to have the whole foot for the tile, so we're not going to connect our line because we don't include those numbers. Now let's look at another example to put this idea together. So the Warren basketball team has signed a contract to get t-shirts made for the fundraiser. It costs $25 to work with the company and set up the t-shirt design they choose, and they have to buy each shirt for $5. So how much does the team have to pay no matter how many shirts it buys, well, it has to pay the setup cost, which is $25 to set up the design and work with the company. Then they also have to buy each shirt for $5. So each shirt is going to cost the basketball team $5. So let's use a numeric representation to fill in the table for how much they will pay for shirts. So if they order 0 shirts, 5 times 0 plus 25 is $25. 5 times 1 plus 25. 5 times 1 is 5 plus 25 would cost $30. If they order 2 shirts, 5 times 2 plus 25. 5 times 2 is 10, plus 25 would get us $35. 5 times 5 shirts plus $25 for the setup would be 25 plus 25, so $50. 10 shirts, 5 times 10 plus 25. So 5 times 10 is 50, plus 25 would be $75. $25, 25 shirts, 5 times 25 shirts is 125, plus 25 for the setup fee is $150. And if they bought 50 shirts, 5 times 50 plus 25 would get us $275. So we can use our table to help us create a function rule, and we're going to let T represent t-shirts and C represent cost. So we have our cost, C, equals 5T, because it's 5 times each t-shirt, plus the $25 that they have to pay no matter what. Remember that the function rule is an algebraic representation. Last, we're going to draw a picture or a diagram of a situation that looks like if they bought a different number of shirts. So remember, drawing a picture or a diagram is a concrete representation. So if they are buying 0 shirts, they have to pay $25 for a setup fee. If they buy 1 shirt, they have to pay $25 for a setup fee, plus they get 1 shirt. If they buy 2 shirts, they have to pay $25, that's the one-time setup fee, plus they would get 2 shirts. If they got 5 shirts, they have to pay the $25 fee, and then they would have 5 shirts.